Okay, so we are now going to start the exercises. In this first one, first of all, we have to decide whether this series is convergent or divergent. And in fact, we have already done this in one of the examples in the text. The series this is divergent. To see why, you can of course go back to this example. And you already know by now why that is so. That is because this limit does not exist had this series been convergent. This limit should have not only existed, but it should have been equal to 0 by the zero test. Since that is not true in this case, so this is divergent, and this is precisely what we have discussed in this example. Okay, now we come to the next part of this exercise. In the next part, we are being asked to resolve the difficulty that we encountered in example 122. If you recall, way back when we started things, there was one section where Professor Tao discusses some examples where in each one of them things go wrong because of our careless use of the rules of calculus. And one such example was this one, which treats infinite series in a very careless manner and ends up having nonsensical results. So now the time has come for us to resolve these difficulties. So one of the series, in this example we saw two series. One of those series is of course this one, and the other one is the series which goes like this: 1 plus 2 plus 3 plus 4 and so on. So we write like this: this series is one of the two series in example 1, 2, 2. This series means this one. The other one is this. Okay. Let Sn be the sequence of partial sums of the series this. Then, from using a well-known formula for the sum of the first in positive integers, we get this. Then Sn is equal to, by definition it is this, the finite series this, and by that formula this equals n times n plus 1 divided by 2 for all positive integer n. And you can clearly see from this expression that the sequence of partial sums Sn is not bounded, since this sequence is not bounded, so it cannot be convergent, because we know that convergent sequences of real numbers must be bounded. Not bounded, and hence is not convergent. So the sequence of partial sums is not convergent means, by the definition of convergence, the actual series itself is not convergent. Thus is divergent. So what went wrong in this example is that when we considered these examples, I mean this series in this example, back when we were considering those things, we erroneously assumed that the series in question are convergent, that is, each one of them has a sum. Actually they don't have a sum in the ordinary sense of having a sum. So the mistake we made in example 1 to 2 is that we assume the series to be convergent, which they are not. So that was the difficulty that we have in this example. So that's just it, that is the solution. Now the next part. And in this one, I think we have to prove one of the, yes, proposition 7 to 5. And hint is given. Use proposition, which one? 6, 1, 12 and Theorem 6.4.18. Six means from the 6th chapter, that is consequences. So the thing first we will do is we will recall the statement of this proposition, and then we will start solving the exercise, that is we will prove it. So we first recall the statement. Let summation of an, where n varies from m to infinity, be a formal series, formal infinite series of real numbers. Then this is convergent if and only if there is an equivalent condition if and only if for every positive real number epsilon there exists an integer n greater than or equal to the least value of the index n, that is m, such that the absolute value of this finite series an, where n varies from p to q, is less than or equal to epsilon for all integers p and q greater than or equal to n. Okay, so this is a necessary and sufficient condition for the convergence of this series. So let us now start proving this in the solution. First of all, what we will do, we will consider the sequence of partial sums of this series, and then the convergence of the series, of course, is nothing but the convergence of that sequence of partial sums, which in fact is equivalent to that sequence of partial sum being a Cauchy sequence. So let us, okay, so before we mention that Cauchy condition, we have to take the sequence, we have to define the sequence of partial sums. Let Sn be the sequence of partial sums of this given series. And now we mention that Cauchy condition, which is some theorem. What is its number? 648. Oh, so that is this thing that Tao is talking about. by theorem 6/418 this is convergent if and only if this is convergent, and hence this is Cauchy. So now instead of talking about convergence of the series, we will talk about the Cauchiness of this sequence of partial sums, because they are one and the same thing, right? So first of all, we assume that Sn is a Cauchy sequence. That means we are actually assuming that the series is convergent. Under that assumption, we have to prove that this thing happens, these things happen. So first, we assume that the sequence is Cauchy. So for any positive real number epsilon, we will now get something from this Cauchiness. There exists an integer n greater than or equal to m such that we know what we can write here. We can write something like this: Sn minus Sm, this numerical difference, is less than or equal to epsilon for all integers n and m greater than or equal to that stage. Okay, so it just simply means this, that if you are okay, we cannot take 1 and 2, right? Things are starting from m. Okay, so the original sequence of partial sums goes like this. So what we are saying is that as we choose one epsilon, then a stage will appear. Such that if you choose your two terms of this sequence from this stage onwards, then the distance between any two such terms is less than or equal to epsilon. So the things are getting closer and closer to one another in this manner. That is Cauchiness. But now we will not in fact write the general condition here, but we will write something special. Summation an, where n varies from p to q, because that's what we want, right? We want to show that this thing is less than or equal to epsilon when p and q are greater than or equal to some integer. Now this thing, it turns out, is sq minus sp minus 1, and that is less than or equal to epsilon for all integers p and q, such that I have to get rid of this. Such that both p and q are greater than or equal to n and q is greater than or equal to p. Okay, not exactly p and q, but q and p minus 1. So what have we written here, and how are we exactly using the condition that this sequence is Cauchy? Cauchiness has been used here in writing this inequality. You see, originally Cauchiness is giving us this, right? Sn minus Sm is less than or equal to epsilon for all n and integers n and m greater than or equal to n. Now, in place of n, we are choosing q, and in place of m, we are choosing p minus 1. We can do that. I mean, instead of choosing n and m, you are choosing something else, q and p minus 1. So, just simply considering that q and p minus 1 are greater than or equal to n, you have this inequality. The absolute value of sq minus sp minus 1 is less than or equal to epsilon. That's it. But you see this additional inequality here. Because of this inequality, this difference, numerical difference, is actually equal to this finite series. And you already know from our results on finite series how this actually equals this. This is because, you see, if you look carefully, you will notice one thing. If you consider this, say, n varying from m to q, okay, this finite series, then by the definition of our partial sums, this is nothing but SQ. But this thing can also be written like this, and this is where one of those rules of finite series come into play. N varies from m to p minus 1 plus summation an, where n varies from p to q, that is equal to SQ. You know which one we are using here. We can write this finite series as a sum of two other finite series where the index n varies like this. Now again, by our definition of partial sums, this thing is nothing but, well, not this thing, but this thing is what you see here, but this first thing, not this one, okay. This first thing is nothing but SP minus 1. So that is how Let me use that part also. So from this you see that Sp minus 1 plus this is equal to Sq. So that means this thing is equal to Sq minus Sp minus 1, and then take absolute value on both sides. Doing that you get this. But in order for this to make sense, we need Q to be greater than or equal to P. So now we know exactly how we are getting all these things from the Cauchiness of the sequence of partial sums. Now in particular, we have this thing less than or equal to epsilon. Now we need not bother about this numerical difference, because all we wanted is to link this thing with epsilon, and that we are getting here. So now we will just think of this and epsilon, and of course these conditions. So in particular, from all these things we are getting this inequality for all Q greater than or equal to P greater than or equal to n plus 1. Why? How? If P is greater than or equal to n plus 1, then P minus 1 is greater than or equal to n, and here Q is greater than or equal to n plus 1. So automatically Q is greater than or equal to n also. That is why we are saying in particular. And additionally we are also having Q greater than or equal to P. So here we have combined all these things together like this. Okay, but see, we are still not done, because we have this inequality Q greater than or equal to P. In the original statement, such a relation between Q and P is not given. Q and P are just some integers greater than or equal to some stage n. So that means we still have to consider that case where Q is less than P. So now we are going to consider that case. But that case is almost trivial. When Q is less than, let's write it like this. P is greater than Q and Q is greater than or equal to n plus 1. We have this thing n equal to P to Q. Now with this inequality, P being greater than Q, what will this finite series be? We already saw in the definition of finite series that in that case this finite series is 0. It has the value 0, and 0 is less than or equal to epsilon. Actually strictly less than epsilon, but if strict inequality is given, that implies ordinary inequality, but not the other way around. So in this case also we are getting what we want, namely this absolute value being less than or equal to epsilon. Hence this is less than or equal to epsilon for all integers p and q greater than or equal to n plus 1. You may ask one more thing also. In the given statement we have n, but here you have n plus 1. This n plus 1 is some n, right? And there is one more subtle thing. Note that we have carefully considered p minus 1 to be greater than or equal to n. And what is this n? This n satisfies this inequality. That means p minus 1 is greater than or equal to m, and that is why the partial sum s p minus 1 makes sense. By definition it is this. Because of this inequality, this thing makes sense and it's not zero. Makes sense means it is a term which actually appears in the sequence of partial sums. That's what I am saying when I am saying it makes sense. So that means we have proved one half of the proposition. Now we prove the converse. Conversely, assume the condition given in the statement. That is the condition that for every epsilon there is an n for which this and that happens. That's that thing. So now you have to prove that the sequence of partial sums is a Cauchy sequence. We now show So for showing that this is a Cauchy sequence, we need to take an epsilon and all those things. So choose epsilon greater than 0. Then by our hypothesis, by the assumed condition, there exists an integer m greater than, if you want you can take n here also, that is not a mistake, but we decide to take another, we use another symbol m, such that this thing is less than or equal to. Now cleverly, instead of taking epsilon, we take epsilon divided by 2, because that is also a positive real number for all p and q greater than or equal to m. Okay. Now this implies that for all p and q related like this: Q greater than or equal to P greater than or equal to M plus 1. So that means now we are considering a special case of these inequalities that come from our assumed condition. So for this type of P and Q also, note that when P and Q are like this, then also they are both greater than or equal to M. In fact, both of them are strictly greater than this capital M. So for them also these inequalities will be true. But now, because of this inequality, Q being greater than or equal to P, this term becomes just like before, SQ minus SP minus 1. Again notice that SP minus 1 is an actual term in the sequence of partial sums, because P minus 1 is greater than or equal to M and M is greater than or equal to small m. So P minus 1 is greater than or equal to small m, and this thing equals that is less than or equal to epsilon divided by 2. Okay, so this much we have got, and still under all these conditions also there is a special case, namely when P is equal to Q. In particular, when P is equal to Q, we have, so you just put this thing here, SP minus SP minus 1 is, okay, I can write because anyway I need to write that thing, no? So I can write it at once. The absolute value of AP, but AP is SP minus 1. So this thing is less than or equal to epsilon divided by 2 for all P greater than or equal to M plus 1. Okay, so we have got two things. One of them is this difference being less than or equal to epsilon by 2, and the other one is this thing being less than or equal to epsilon by 2. So for all Q greater than or equal to P and P greater than or equal to M plus 1, we have okay, now we are back with general P and Q. Okay, now P and Q are not equal. This is a special case in which, from which we are getting this thing. So that we just we are going to use that separately. Now again our Q and P are just related to each other like this, and they are also related to M in that way. So here SQ minus SP, this thing is going to be equal to SQ. It does not feel right to write the modulus separately, one part here and one part there. This is equal to SQ minus by the definition of the partial sum SP. Note carefully, we are not considering SP minus 1 here, we are considering SP. This is SP minus 1 minus AP. It should be clear why we have this. This is because if you apply the definitions of these partial sums SP and SP minus 1, you will see that SP equals SP minus 1 plus AP. That's just it. And now you use the triangle inequality. So this thing is less than or equal to SQ minus SP minus 1 plus, let me show it fully, plus AP. Okay, because inside the absolute value you can get rid of the minus sign if there is any. Now, because we have these inequalities, so this thing is less than or equal to epsilon by 2, although I have wrapped that up. You remember that this is how we started things here and then we got this. So this is less than or equal to epsilon by 2, and again you see this thing is less than or equal to epsilon by 2 when P is greater than or equal to m plus 1, and that is true here. P is in fact greater than or equal to m plus 1, so this is also less than or equal to epsilon by 2, so this is equal to epsilon. So when Q and P are related to each other like this and both of them are greater than or equal to m plus 1, then this difference is less than or equal to epsilon. Now, if the opposite inequality is true, if P is greater than Q and Q is greater than or equal to m plus 1, then by what we have proved above, that is this thing being less than or equal to epsilon, we have okay, so SP minus SQ, this thing equals, because of the absolute value, SP minus SQ, but this is less than or equal to epsilon. How? Because this thing is less than or equal to epsilon when Q is greater than or equal to P, and we have switched the roles of P and Q here. So this, you just think of P here and Q here, so that will be less than or equal to epsilon. Thus we have proved that the distance between SP and or if you want you can write Q first, because that's how we are writing it, right? SQ minus SP is less than or equal to epsilon for all Q and P greater than or equal to m plus 1. So whether Q is greater than or equal to P or less than P, it does not matter. We consistently get this thing when both of them are greater than or equal to m plus 1. So for that chosen epsilon, you have found an integer m plus 1 greater than or equal to m. M itself is greater than or equal to small m, so m plus 1 is also all the more so greater than or equal to small m, such that this numerical difference is less than or equal to epsilon for all P and Q starting from that stage. Hence, the sequence Sn is a Cauchy sequence. And consequently the original series is a convergent series. So if we consider the conditions given in the statement of this proposition, then if those conditions are true, then the series is a convergent series. So this completes the solution and proves this theorem. Next, use this proposition that we have proved just now to prove corollary 7 to 6. So corollary 7 to 6 is that zero test for convergence. That is, if an infinite series summation an is convergent, then the limit of the terms an should be 0. It should exist and it should be 0. So let us consider this series. Let this be a convergent formal infinite series. Formal infinite series. Choose a positive real number epsilon. Then by our proposition, there exists an integer n such that the absolute value of this finite series is less than or equal to epsilon for all integers p and q greater than or equal to n. So in particular, when p is equal to q, we have the absolute value of ap minus 0, which is equal to the absolute value of ap, but that is equal to summation an n varies from p to p. This is less than or equal to epsilon for all p greater than or equal to n. So see what we have achieved here. We have been able to show that for any epsilon, any chosen epsilon, a positive real number, there exists an integer n greater than or equal to the least index m, such that the distance between ap and 0 is less than or equal to epsilon whenever p is greater than or equal to n. So this directly implies from the definition of limits of sequences that ap converges to 0. This implies limit ap equals 0 as p approaches infinity. If you want, you can write n in place of p, because p is after all a dummy variable, so it can be changed. And that is just your zero test. The original series is convergent, then this limit must exist and must be 0. So this completes this solution. 3 more exercises are there which we will do on the next Sunday. So with that, I end this video. If you want to comment on these things, you can write in the comment section below, or you can mail me at my usual address. The link will be there in the description. And this coming Tuesday, let us once again go to field theory. So that will be all for tonight. So see you on Tuesday with field theory. Until then, this is me, Lucifer, from a mathematical room. Have a nice day.